Hi, this is a follow-up to the previous video that I did about an RF signal generator that I built. I built it from that magazine article. And last time I ran the frequency counter on it and concluded it was working. And then I decided I'd put the scope on it and get a closer look. Of course, the moment you declare something working, you'll find out it was completely not working. Okay, so a few changes since the last time we showed off the circuit. The first thing I realized that these two pots I had screwed up. I thought I had a box that was entirely full of linear pots. I don't remember ever ordering an audio taper pot in my life, but somehow audio tapered ones got soldered in. And you may have noticed in the previous video when I'd get up to about there, you know, we started jumping really fast in frequency. Of course, that was because it was a logarithmic scale. So got rid of those and put in some linear pots. One of these days I will go through the junk boxes and clearly find any audio taper pots and put them in a special place of their own. The other thing that I've done is I've got rid of the additional transformer that was in here that was powering a negative supply for my op-amp board. So basically there I learned I do not need a positive negative op-amp to amplify an AC signal. I posted on EEV blog, I said, you know, I got a single transformer, I want to amplify this AC signal and I want it to be rail to rail, and people said, well, you don't really need that, just, you know, bias the signal up so that it's within the range of your single supply op-amp. So I did that. That'll be explained in the blog someplace with the revised circuit diagram. That worked very nice. Got rid of the additional power supply, the additional transformer, simplified everything throughout. The other thing is I revised the circuit board based on what I'd learned about the Galley 55 amplifier. And then only to realize that the revised circuit board didn't work either. So I have a whole blog post on this on the website that the Galley 55 it's very susceptible, I believe, to parasitic oscillations from bad layout, and that's what I'd done. I'd, you know, plopped it on there. I had some long traces, some skinny traces, and I think the thing just started oscillating up in the gigahertz range. That caused the gain to drop way down, and because, you know, it was oscillating up in the gigahertz, and I have a 100 megahertz oscilloscope, I couldn't even see it. Fortunately, the guy who wrote the nuts and bolts article, he was very helpful, pointed that out, and I fixed my layout and managed to get that to the Galley 55 working. So let's start by ramping this thing through its ranges. Here we are on the lowest range, which is goes from 137 kilohertz on up to 428. The wave near very low voltages, it always starts to distort. I think this you know, I've just got the potentiometer going a little bit past what's really the usable range of the VCO that I built. So let's call it realistically about 150 up to 430. You know, you can see we're getting a pretty good sine wave. Peak to peak voltage is 2.3 volts. That's quite a bit. I haven't taken the time to set the AGC resistors, get every band working the same. I still want to do that. I did want to go into as good a time as any to talk about the connection testing methodology a little bit here. I have a BNC cable. It's hooked directly up to the output capacitor out of the MMIC amplifier, and over on this side we have a 50 ohm inline feed through terminator. So the Galley 55 is supposed to be 50 ohm impedance. We've got a 50 ohm cable. We've got a 50 ohm terminator. Throughout these measurements, I've tried with other testing methodologies, and the results are similar. So we'll just use this since it's the simplest. Another thing I've done is I have a scope probe set up with a with a BNC adapter, you can just plug it in. So done that, you get about the exact same results. So back to going through the bands. The next one up, we've got about 226 to about 645. Again, you can see, nice decent waveforms on the scope. A little bit distorted, but not horrible. Going up, 360 up to about a megahertz, and 2.3 volts. So we're got a pretty stable output voltage through the first three ranges. Fourth range here, we're getting 430 kilohertz on up to 1.1 megahertz. We could probably do away with that range. Part of this is I just put, what inductors I had in here. Next one, let's call it about 900 up to 2.5 megahertz, getting about 2.3 volts peak to peak. There's the next range, going from megahertz and a half on up to 4 megahertz. Then we've got another range of about 3.6 on up to 11 megahertz. So that, in particular, when I have some of those pesky tube amplifiers that need to be tested to 10.8, we should be able to precisely dial in 10.8 with, of course, in the fine controls. See how close and stable we can get it. Oops, overshot just a hair. There's 10.801. The Rigel's also reporting 10.801 on its built-in frequency counter. Looks pretty good. Seems pretty stable. Still getting 2.2 volts. The next range, we've got 8 megahertz up to 22 megahertz. 2.2 volts all the way across. Not the world's best sine wave, but certainly a pretty darn good one. All the way throughout the range. Let's go up one more. This one we've got 20 megahertz. Then we'll ramp it up all the way up to 56 megahertz. Now we did, on this range, we finally do start to see the output level drop a little. First half of the range is about 2.3 volts. Tail end of the range is about 2 volts peak to peak. That's pretty darn good. Now this inductor here is green Radio Shack insulated solid wire round in coil. It's pretty good. We're up to about 80. Pretty good across the board from 30 megahertz on up to 80 megahertz. The next inductor is just a straight piece of wire, and it starts out at 38, goes up, we're about 87, 90. Now you can see when we get around about 90 megahertz, so move the horizontal a bit to the side, we're starting to get some divergence here. So what, there's about clean all the way up to 80. Then as we go up, 85, 87, 90. I mean, look at that. We've got, this fuzzy waveform. There it's particularly bad. So that is the current problem that I'm trying to debug. I don't know if that's good enough. Certainly seems kind of nasty. There, you can get a better look at it. It's all throughout this 80 to 100 megahertz or so. And then it's, after you get past 100, it kind of starts to pull itself back into shape. So we get all the way up to 112 megahertz, which will just about cover the whole band that you might need for aligning a FM radio. It's just that little, I mean, look at that. That's pretty ugly in there. Fussing around with the coax here, just touching it, grabbing it. It seems to do a little something. I'm gonna zoom in on that waveform. It's as close as my zoom lens goes. So there's all the way down. You can see a little bit of divergence there, even at 40. Yeah, so that's that first area on the pot. So you go from 42 on up, and that's where we get into that 86, 88, 90, 96. And look at that, right in here at 102. That's pretty ugly. Let's go math. Guess it's nice to be able to see what the spectrum analyzer has to say about it. So the spectrum analyzer, there's our 100 megahertz there in the middle. We can see there's some junk going on, but it doesn't really look like anything that explains that huge thing. So here we've got 100 megahertz, this is 25 per division, so we've got 125, 150, there's a harmonic of some sort. 150, 200, there's something. That's around 50, yeah. I don't know, so, if there's someone watching the blog who really understands what's up with this fuzzy waveform I'm getting in here, I'd really like to know. I've tried adding bypass capacitors, tried doing all kinds of stuff, but I cannot clean that out of the signal. For our next experiment, let's see how well the AM modulator works. So I have a very old BK precision function generator. Let's see if we can set it to send out an 800. It's a little bit of overshoot. 800 hertz. Okay, I'm going to call that good enough. There's about an 800 hertz signal coming out of that, hooked up to the modulator in jack here. I have the modulator disabled. Let's turn the modulation level all the way down. If I start ramping up the modulation, see, look at that. We're getting some modulation in our megahertz wave. Let's bring that down where we can see it really good. That is the I didn't mean to touch the RF control. Had that dialed in at a nice megahertz too. This would be something to be said for having different sized knobs. Okay, here's the modulation level. So there we've got no modulation. Start bringing in modulation. You can go pretty crazy with it. Yeah, so that AM modulation appears to work. Here's a quick overview of the RF circuit board from the RF generator. The large chip here is the MC1648 voltage controlled oscillator. Buried over here is the varactor diodes. It's a 2-diode package, so there's 3 terminals, one for each diode and one common. Over here is the Galley 55, the MMIC amplifier. There's a resistor here that sets the automatic gain control. Power comes in up here in this header, so there's both a 5 volt and 24 volt. The 24 volt goes through these 2 bypass capacitors and then into this resistor, which reduces the current down to 50 milliamps. Then it feeds into the Galley 55, and then there's a capacitor that couples the output signal into this output header. So over here we can see that in one of my attempts to diagnose what was going on with the weird fuzzy waveforms, I added a whole bunch of extra bypass capacitors and I soldered them right onto the resistor so I could kind of get them as close as possible. I put it in a 0.1 microfarad, 0.01 microfarad, and 0.001 microfarad. There might have been some incremental gains from that. I don't really know. Over here I have the voltage signal for the VCO. It comes in, goes through a 0.1 microfarad capacitor, a 47K resistor, and into the common terminal on the varactor diode. These 3 pins here go to the selector switch that is used to select the band. So there's a ground, and then there's each side of the inductor and the selector switch. These 3 capacitors take they amplify the tank signal and provide it to the MMIC. There's plenty of bypassing throughout, so you know here's a 5 volt bypass cap. Here's another 5 volt bypass cap. Those are 0.1 UF ones, 0.1 microfarad. Here's a 1 microfarad. I've got another 0.1 microfarad and a 0.01 microfarad. On the back side here I put another maybe 0.001. You know, I tried to bypass the heck out of the thing to see if that would help. It didn't seem to have a big effect. And that's basically the RF board. If we flip it over, we can see some. See, there's actually a ground plane throughout. You can see where I added on some more bypass capacitors. I did away with the PC board traces going to the varactor diode, thinking that, you know, maybe we would do better if we had a nice solid conductor rather than those tiny traces. I don't know that you can see that close on the Galley 55, but the fix I had to not producing the gain was that rather than having PC board traces going from these input and output capacitors to the amplifier, I took and I soldered the capacitor directly onto the amplifier. If I didn't do that, then it would go into that parasitic oscillation mode and lose all the gain. Yeah, I'm going to go quickly through the changes I've made to the op-amp board. So over here we can see that we have a single op-amp. Originally I used an LM358N. I've since changed that to a TLC 272. You can also see that I was running it off -12. I actually added a pad so I can just short that and make it a single supply op-amp. Short that pad and run it from ground. This whole section here does the signal processing on the 2 potentiometers. So they come in through these 100 kilo ohm and 1 mega ohm resistor. They're summed. There's provision for a frequency modulation. I don't have this on the supply, but I have added on my latest prototype. A board is coming that will have a Zener diode to keep the reference voltage for the pot very steady. There's lots of bypass capacitors. And here is the latest change I made, what I was talking about with the AM modulation signal earlier in the video. So our AM modulation comes in here. This is right straight out of the Nuts and Bolts magazine. These two diodes do some clamping. But what I did is I put some jumpers in here, and I added this extra section right here. These two 100K resistors and this capacitor. What this does is it AC couples this signal. So this could be 1.4 volts peak to peak centered at ground. It's going to come in here, it's going to get AC coupled through this capacitor and then pulled up by this voltage divider. So rather than an AC signal about ground over here, we now have an AC signal about 6 volts. So 1.4 volts peak to peak centered at 6 volts. Then we can go through this jumper and right into our single supply op amp. And then it comes out and it's AC coupled again, goes into the 1648 chip. So anyway, that was the change that I did to get rid of having to have the dual supply op amp and simplify the circuit.